Okay, so this is page 1014 of the book, and today we are going to start discussing another family of filters named after another mathematician that studied these types of polynomial, Russian mathematician, and he actually came up with this in the context of steam engines back in the 1800s. So we all know math is pretty old, and this type of filters have this type of response. Okay, it has a discernible ripple in the passband, and it's that ripple is has the same amplitude throughout the passband. So the amplitude is what we call an equiripple response. On the transition to the stop band, it has a monotone transition. So sort of a constant slope. Okay. And then where this starts, where the equiripple starts, has to do with the number of with the order of the filter. Okay. So if n is odd, it starts right at 0. If n is even, then it starts at what we would call minus a max. So below from 0, the amplitude of the equiripple response. So the also the number of extrema of the equiripple is equal to the order of the filter. Okay, so for example, we see that this filter is of order 5, or a fifth order filter, because it has 1, 2, 3, 4, 5 extrema in the passband and in the equiripple. So this is an all-pole filter, meaning that all zeros are at infinity, and we only have poles.
Only for this case, right? That it's 5. But it could be.
I'm sorry?
It's only for this case, right? That it's order number of 5.
Yes. So the number of extrema would be equal to the order. So if your order is, in this case, less than 5, you'll have fewer of these oscillations, and if the order is higher, then you'll have more in the passband. Okay. So that's what we're going to start talking about today, covering that family of filters. So again, we're going to talk about Chebyshev filters, and I want to list again these important observations. So we have equiripple response, monotone transition, three, we have that the magnitude of the response at DC is equal to 1 for the order, if the order is odd, and would be or be related to A max for n even, and another one is that the number of extrema in the passband is equal to n, and the last one that I mentioned was that all zeros at infinity, which implies that this is a all pole filter. So those are the important things to remember. Okay. So if we utilize the Chebyshev polynomials and take the magnitude of that after substituting S with j omega to get the frequency response, we'll find that the frequency response of this type of filter is best described by this equation. And this is a low pass case. So that's why we have only one omega sub p, which is the cutoff frequency. And all this is the denominator of 1. So that would apply for the passband. And then for the stop band,
Wait, Dr. Hernandez, is the cosine squared multiplying e squared or multiplying 1 plus e squared?
So we need a bracket over here. So the cosine square is of this quantity, and it multiplies epsilon square.
Okay.
Does that answer that?
Yeah, it does. Thank you.
All right, great. All right, so that's for the passband. Okay, so this is the passband, and then for the stop band, we have this expression. So notice that this is hyperbolic cosine. Inverse hyperbolic cosine of omega over the cutoff frequency, and then the square root covers all of this, and that's a denominator of the fraction with 1 in the numerator. So that would be 4 okay. So that describes in its entirety the response, the magnitude response in the frequency domain of these types of filter. One relationship that makes this work, okay? If you remember those two equations, or if you can look at them in your notes, is that inverse cosine of 1 is equal to inverse hyperbolic cosine of 1. So that would be when omega is equal to the cutoff frequency, and that makes the equations the same. Okay? So additionally, at the cutoff frequency, if omega is equal to the cutoff frequency, then the magnitude is 1 over the square root of 1 plus epsilon squared. That's another important observation, okay? And what that means is that A max for this low pass filter is 10 log of 1 plus epsilon squared, and we can find epsilon, which is an important parameter of the filter, from solving for epsilon in above, and we get this relationship. So remember that this is a specification that you're given, and you start constructing this transfer function by finding the parameters of the transfer functions, and one of them is epsilon. So this is what you use to find epsilon. As a function of omega, if we go back to the transfer function, the actual polynomial, or an equation that is related to the polynomial and to the amplitude, is using the same expression as before. And here we have not omega p, but omega s. This is at the bottom of the transition. At the bottom of the transition, when we actually have a stop band frequency that is different from the passband frequency. So we would use this equation to relate those two. We have two brackets. So this the next to last bracket would be for the hyperbolic cosine square, and then the last one is for the log. So this expression can be used to determine n for both conditions, for two conditions, for a given A for attenuation, so because this is an equation for the attenuation, and also it will be whatever the n that comes out of this equation would also take into account how fast you want the filter to transition, how selective you want the filter to be, because here we have the ratio of WS and WP. So the closer these two are, n is going to come out to be higher. Okay? So n is the lowest possible. You also want to have n as low as possible because that simplifies your design, such that at the stop band your attenuation is greater than the minimum attenuation that you're trying to accomplish. And as n increases, the behavior approaches the ideal case. And the ideal case is where omega s and omega p are the same. And you just have basically a step in the response. So now that we have n and epsilon, we can use those parameters to find the location and assign the poles of the filter. We're going to have as many poles as n. So a given pole, p sub k, is going to be given by all parameters that we know. And then there's going to be a multiplication here to the following factor, hyperbolic sine, that's going to be the real part of the pole, and then the imaginary part with j there, oh, one correction here, this is not raised to the minus 1, that's not an inverse. Oh, sorry, I was looking at the wrong place. It is an inverse. This is the one that I was, so actually put that back in there. Just like this one. And that is the imaginary part. And these poles, they hold for k and so forth. So that's how you would find the poles of the filter. Each complex conjugate pair is going to have a natural frequency. So for each complex conjugate pair is going to have a natural frequency omega naught, which is going to be the norm or the magnitude of the pole. And also, to introduce the quality factor of the pole, we have the relationship that the natural frequency of the pole divided by 2 times the quality factor of that pole is equal to the negative of the real part of the pole. And once you have those parameters, now we can construct a transfer function in S, which is going to look like this. So for these types of filter, we're going to have the poles in the denominator multiplied by epsilon and 2 to the n minus 1, and then we're going to have the poles or the pole factors up to n. And the numerator is going to have a scaling factor, which is going to call it K, capital K, that is going to multiply the passband omega raised to the order of the filter. So to summarize, the design procedure, which is really what we also went through, first, as we did, we determine epsilon from our specified Amax. Then we determine the order of the filter now that we have epsilon, and we're also given a stop band frequency and a passband frequency. Then we determine the poles, and last we can determine our transfer function. So again, going back to what I discussed last time, this is just a mathematical formulation, or what we also call mathematical prototyping or modeling. You have to still go and come up with, once you have this T of S, you have to come up with your actual topology, your circuit, and test it and reconcile it with the mathematical prototype so you can get equations or design equations. And again, this is called the realization of the circuit. And those would be design equations that relate the coefficients in T of S to another T of S that has coefficients as group of component values, which would be your R's and C's, assuming that you're not using inductors. There are good reasons not to use inductors, other than for modeling and prototyping. So that is the Chebyshev filter, and all the associations that we made last time. The fact that if you want the high pass, you can basically subtract the low pass from 1, and you can also come up with well, in this case, this is an all-pole filter, so specifically they are not good for bandpass necessarily, but you can get a high pass by subtracting the low pass response from 1. So that is the Chebyshev filter, specifically the low pass. Now let's look at another type of filter formulation. We can get this mathematical prototypes from in many ways. So you've seen two so far, the Butterworth and the Chebyshev, based on families of polynomials or rational polynomials rather. Let's look at another formulation. This is a little bit more specific. This is a second order, so this is another prototype where we're actually going to be using circuit elements to prototype a filter. But what we're going to be seeing, this circuit that we're using to prototype, is not how we're going to build it in reality. All these filters are going to be built at the circuit level, and we'll see that later as active filters that contain resistors, capacitors, and op-amps. And we'll mention why we want to keep away from inductors. But we can use a circuit to prototype a system that is based on capacitor, resistors, and inductors. So specifically, this one will show a second order passive. So again, no op-amps here. Filter prototype that is based on what we call an LRC resonator. And this is shown. It's a good time to switch to the book. So this is a second order resonator with a resistor, a capacitor, and an inductor, and we can drive it with a current source and take our output across the parallel combination, or we can drive it with a voltage source between our reference and the inductor and take our output at the across the parallel combination of the resistor and capacitor. So that would give us different prototypes that we can have. So but the point is that it is a parallel combination. Okay. So as you saw, we have a parallel combination, and because of that, it is more convenient to work with the admittance. Okay. And we're also going to be, since we want a transfer function in the S domain, we want to work with the Laplace impedances or Laplace admittances. So we know, so how do we come up with this? So this should be a refresher. So we know that the current in a capacitor is equal to the capacitance times the derivative of the voltage across it, and we know that the voltage across an inductor is equal to the inductance times the derivative of the current through the inductor. So we also know then that, and we discussed this last time, the S complex variable in the S domain maps to the time domain as a differential. So in each case, we can have that I of S is equal to C S V of S for the capacitor, and that for the inductor, V of S is equal to L S I of S. So if we want the Laplace impedance of the capacitor, that would be V of S over I of S. So C of S would be 1 over SC, and for the inductor, C of S would be L times S, and then the admittance is the reciprocal of that. So for the inductor would be 1 over LS, and for the capacitor it would be SC. So we want to work with this Laplace admittance and impedances. So when we apply our circuit design, our circuit analysis equations, sort of like nodal analysis and things like that, we come up with an expression in the S domain automatically. And that's what we're going to do with this resonator. So again, we want to work with the admittance because of the parallel combination. So we're going to write that we want, in the case that we are driving with the current, we're going to be using that that configuration. So that would be 1 over the admittance. And admittances in parallel, they add. So essentially, that would give us 1 over the total admittance of the parallel combination is just the sum of the admittances. So we said that for the inductor, it was 1 over SL. For the capacitor was SC, and for the resistor, still, since there are no derivatives in Ohm's law, so for the resistor, the admittance and in the S domain as well, it's just the conductance, or 1 over R. Okay, so we can massage that a bit, and we come up with our second order Laplace transform of that resonator. And here we have S over C. So we can see that the denominator is the second order equation that we want to relate to these important parameters that we have been referring to in all the filters, which is the natural frequency and the quality factor. So because they are related to the behavior of the filter, so we can write that denominator equation as the same factors of quality and natural frequency that we have been or center frequency that we have been using before, like so, and then just by inspection, which is again what you would do. And here we have something that comes from the system and something that comes from the circuit. In this particular case, we have that and so therefore and the Q is equal to, so these two equations, if you were going to build this circuit, we would use them to find the components, but we're not, because this is not the circuit that we want to build. We just want to use this resonator as a prototype and then relate that back to the system, and ultimately later we can relate it to an actual circuit. So one thing that before we go on further, we want to talk about the realization of the zeros for specific filters. And at the beginning of the chapter, we talked about how the zeros influence the type of filter that we have. So we're talking about whether we have a low pass, a high pass, etc. And we want to do that by, in the case of this resonator, we're still working with the resonator, by forming a voltage divider. And whatever we have in different legs of the voltage divider is going to give us the characteristic of the filter, and also the zeros. So let me show specifically what we're talking about. We have this this resonator here, that has a capacitor, an inductor, and a resistor. If we form a voltage divider, let's say with some impedance, one of those, and I'm going to call this impedance the zero impedance, and then the other ones that are in parallel are going to be the, let's just call it Z other. And now I'm going to take my output from here and I'm going to input my voltage from there. So you can see that this is just a voltage divider. So V out over V in, which is also my transfer function, is going to be, sorry, I got this two mixed up. This is my zero, let's call it other here. Is going to be my zero impedance, because that by the sum of both. So depending on which one I put here, I'm going to get the pulse and therefore the behavior of the filter. Okay? And this can also be written in terms of an admittance if it's convenient. So without any loss of generality, this will become y0 divided by yz plus y0. Okay, depending on what I'm doing. So just to be more clear, what I'm saying is that disconnecting a component of the parallel combination and this is an important observation, disconnecting a component of the parallel combination does not change the natural response. Okay, remember from circuits that this type of filters have a natural, has a driven and a natural response. So when you're looking at just the natural response, which would be the step response, not the steady state response, it doesn't matter which one you are driving, it always looks like the same parallel combination, and that natural response does not change. And if you remember about the classic two-order natural response, that natural response are the poles. So the poles are not going to change. After all, it is a second order filter and the pulse gives you the selectivity. It's going to have the selectivity of the second order To get more selectivity, we have to change the order, but specifically we're talking about a second order here. So that doesn't change. Okay? And the reason that you always get that parallel combination is that when you are calculating that natural response, so let's put naturally here, the input voltage is a short. That's how we compute the natural response. We basically substitute the sources by their internal impedance. So we can look specifically at trying to get a low pass filter from this second order prototype. So let's look at doing that. So here we have different filter structures depending on what we make the zero impedance. Okay. So this would be the impedance that gives us the zeros. If we configure it this way, we have a low pass. And you can see how that comes along. If we put the capacitor and the inductor in parallel as the zero impedance, we have a bandpass. If we put the resistor as the zero impedance, we have a notch or a band stop. And if we want to formulate a general notch, we could do it this way as well. So there are general notches that you can do with two inductors and two capacitors, which are special cases, but we're going to be looking at these different types of realizations. So first we're going to look at the low pass, which is this one here. So let me stop this. So now you know what we're talking about. So that is in page 1032. So let's do that. Our low pass, which by the way is also, if you want the high pass again, you just have to subtract that response from 1. So if we apply a voltage divider, then we get, in the S domain, we get the this equation. And that with some, just to make the denominator for the poles, that second order equation that we had looked at, so remember that this is related This is related to let's see if I have it right. Yeah. So this is related to the natural frequency, and this is related to the natural frequency and the quality of the filter. So that will give us the low pass if we apply that voltage divider, and we know that we can get the high pass from that. So let's look at the band pass. Again, from that configuration that we saw in the figure. And also keeping in mind that if we want the band stop, we can get that from 1 minus the band pass response. But according to our voltage divider configuration, the Laplace transform of the band pass would be and then we can also arrange that So notice that the denominator is always the same. What changes is the numerator, which are the zeros of the transfer function. Any questions so far? Although of course you know that you can ask questions at any time, but this is a good time because we're going to shift gears and talk a little bit about, as we approach how we're going to realize these circuits or realize these filters with real circuits. We want to talk about the issue of inductors. So remember that we have been talking about really efficient filters, and whether it is active filters with discrete op amps or filters that you can realize on a chip in an integrated circuit. And the thing is that inductors, to really get some meaningful impedance with inductors, they have to be bulky. They either have to be bulky at low frequencies, or the frequency has to be extremely high. So with very high frequencies, the inductors become much more feasible. But these frequencies are much higher, so let's say microwave, much higher than what we are talking about here. So this type of analog design that we'll be talking in this course, I would say anything below 2.4 gigahertz, that's pushing it. So since the impedance in the steady state, okay, for an inductor is 2 pi times the frequency times L, to get any meaningful impedance, you either have to have this be very high or this be very high, which implies big. So inductors are an issue with normal sort of frequencies. Capacitors are not. So the impedance for the capacitor is, so a small capacitance and a small frequencies actually, or low frequencies, give us more meaningful impedances. So when you want to work with very high frequencies, let's say microwave, you want to, your circuits to use inductors. Other than that, you want capacitors. And we want amplifiers, so we can make amplifiers with MOSFETs. So we'll see that later on, because MOSFETs is pretty much all we have. And then we can also make capacitors, fairly good capacitors with integrated circuit technology, and even by using MOSFETs, because the MOSFET is really a capacitor. So if I use the gate capacitance and tie the drain and the source together, I got me a capacitor right there. Okay? Because this is your gate electrode, this is the gate oxide, some thickness there, and this is the other electrode, which is the drain and the source tied together. So that's the definition of a capacitor: electrode, insulator, or dielectric, and another electrode. So we want to get rid of the inductor. And what we're going to do next is to look at a clever simulation of an inductor that uses only op-amps and capacitors. And to the driver and as a load, it looks just like an inductor. So that's very convenient. Now it's very complex compared to a single component inductor, but it doesn't matter. The op-amps and even resistors and capacitors are all made with readily available integrated circuit technology that we can make very small, very efficient, and we have a lot of those. So that's not a problem. To trade off the getting rid of this bulky metal-based guy to have a much more complex type of simulator or simulated inductance based on op-amps and other components. By the way, you can make inductors with fairly decent quality, but for high frequencies with semiconductor technology, because we do have metal layers, but again, it doesn't, for normal frequency below 1 gigahertz, it doesn't really work. So that's where we're going. Let's take a look at that, and I'm going to show the schematic of that circuit later. But what we're going to see is that the input impedance of this circuit, defined by the voltage that you apply divided by the current in, is going to look like an inductor. So it's going to have an S, because remember that the Laplace inductance is SL, and it's got a lot of components. So it's got four resistors. I'm sorry. It's got a capacitor, and 4 resistors rather. So if this is my Laplace impedance for an inductor, and that is SL, then this must be L. And I have many degrees of freedom here. And then, so one thing I could do is make all the resistors the same value, okay? And then this becomes, that inductance becomes the capacitance times the resistance squared. And now that I have, if I wanted to build a filter, which, because the inductance simulator or equivalent circuit has op amps by default, becomes an active filter, but I can use it with the prototype of the LCR resonator and use this in place of the inductor. And then I can get a second order filter based on that prototype. Okay. So let's look at some figures related to this. So you can see what the circuit looks like. So page 1035 of the book. You can see what the circuit looks like here. So again, if we look into this terminal here, reference to this terminal here, we'll see an inductive impedance. And if you wanted to follow the actual derivation of this expression, so they do a nice job down here. Okay. The way to follow this is to start with the first number. So basically here you get an expression, okay, of the input current. Then you get an odd equation from here. You get an odd equation from here, okay, and you're using the fact that the op amp has a virtual short at the inputs and so on. So you can, 1, 2, 3, and so forth. Those are the steps, the way they show it, and you can follow the derivation as you study this. So again, you could use this in place of the inductor in the LRC resonator. And you would get an active filter.
Dr. Nance, can you please why we were once avoid using an inductor?
Because they're bulky, and you really cannot make them effectively except for very, very high frequencies in integrated circuit technology, the one that is inexpensive, very easily. I think that what I show is that the meaningful impedance for an inductor, you either have to have a high inductance, which means bulky, high physical size or big, large physical size, or you have to have a large frequency because the impedance of the inductor is S times L or 2 pi FL, and that's how you can see the dependence on the frequency and the inductance. Did that answer that question?
Yeah, it did. Thank you.
All right, very good. All right, so you can work. You can see here that in the resonator we have taken that inductor and essentially we put our inductor simulator, and we have still the same resonator. And depending on, again, how you're still doing the voltage divider, so depending on where you take the output, which is equivalent to how you place and make the impedance for the zeros in the resonator, you get different types of filters. So, for example, this will give you the first one will give you a low pass if you take the output from here, and we just throw in some type of a scaling factor. That's trivial, but here we put the input over here, and essentially we are taking the output in here. That gives you a low pass. If we feed the input on this side of the resistor and take the output after this scaling factor, which essentially is the capacitor in parallel with the whole inductor circuit, you get your bandpass, and then you can get a notch by essentially putting the inductor in parallel with the capacitor here and taking the output of this node here. Okay, so those are realizations of active filters based on the inductance simulation circuit and prototyped after a second order LRC resonator. That would be the right way of referring to those circuits. Any questions? All right, so the next thing that we want to look at is another type of second order active filter, which is based on a two integrators loop. And that is in figure 1423. So essentially what we're going to see is two cascaded integrators, exactly the same. So we have two to get the second order that are going to behave depending on where we tap, are going to give us different types of filter behavior. Okay? So here, at the input of the first one, we're going to have the high pass response. Okay? If we call that the high pass response, then if we integrate that, we get this term in terms of the high pass response. And then if we integrate it again, we get that term of the high pass response. And then if we solve for that, we can do that by using a summing or a summing junction. And then we can put into that summing junction our input voltage here, and we can define the high pass response as our output. So we know that we have to subtract this term, and we have to subtract this term multiplied by 1 over q, and we can come up then with the actual circuit here with the loop. The interesting thing is that we already define the high pass as what's coming out of the summer or the summing junction, and if we integrate that, we get a band pass response, and if we integrate it again, we get the low pass. So depending on where you take your output of this system, you can get any of the filter responses that you want without changing anything. Okay? So this would be second order active filters based on two integrator loop. So basically what we did is we define our transfer function as the high pass response versus our input voltage, and we know that a high pass, we're still talking about a second order, so the best high pass that we can have is some scale factor with 2 zeros at 0, because we really want to reject the DC. This is a high pass. And for the second order, we still can use our familiar second order prototype. That hasn't changed since the beginning of the chapter. And we can essentially get our summing junction equation from this transfer function. So you can see our output here. You can see our first integrator. You can see our second integrator in action, and then from the output of the first integrator into the summer, that's why we get that factor. So then our output voltage for the high pass is precisely that the output of the summer. And if our integrators are inverting integrators, then we get those minus signs for free. So this is exactly the output of the summer. And this term would be the output of the first integrator, the output of the second integrator, and this is just a gain. To get the bandpass, we can define that response and essentially integrate the high pass response twice. So basically, if we integrate twice the high pass response, we are removing the zeros. Oh, sorry. I don't want to integrate twice because that would make it a low pass. So I only want to remove one zero. So for the band pass, I only remove one zero. So that's why it's the that's why it is the output of the first integrator. And then if I further manipulate that expression, I end up with a single zero that gives me that bandpass behavior and also the cutoff frequencies. My poles don't change. What have changed are the zeros. That gives me the filter behavior over the second, our familiar second order denominator. Then for the low pass, that's what I want to integrate twice. So I would integrate twice to remove the zeros at DC so I can get all the DC in. So this would be an all pole filter from that high pass transfer function. And then I get my low pass transfer function again, all poles, so I only have a constant in the numerator of the transfer function over our so that's over our familiar poles denominator. So I think that this is a good place to stop, because we have gone through a lot of examples, and at this point all that we have been doing are mathematical level, system level prototyping of filters. And at this point, so we are halfway through the chapter. So at this point, we're going to shift gears now to realizing these filters with op-amps, resistors, and capacitors, and realizing these prototypes, these systems with actual circuits, and reconciling the mathematical formulation with the circuit analysis equation, which will allow us to calculate the component values. So we're going to start doing that. Not in the same order that we did the mathematical formulation. I think that I'll probably start with the what we just discussed, the two integrator loop realization, because it's closer to the uses the integrators, so you're familiar with Miller integrators, and it's closer to the circuit, so it may be an easier transition there. So that's where we're going next time. So I'm going to stop here and see if you have any questions that you want to bring up.